a few slides, a few words about where I come from. So it's Stockholm, Sweden, and the Royal Institute of Technology, the Department of Fiber and Polymer Technology. And in this department we have different divisions: biocomposites, coating technology, fiber technology, polymeric materials, polymer technology. That is where I have my office, in polymer technology, and then we have wood chemistry and pulp technology. And if you go into our website, there is a movie film where you can actually see me as well in my lab. So if you want to see what it looks like, I won't take those minutes to show you now, but you can go in there and have a look. And this is actually what I'm doing in my research. I'm a polymer chemist from start. I really love to synthesize polymers and use my creativity to change the properties and understand how the design can really influence, and especially the cell material interactions. So we're a lot in our lab. Perhaps 15 years ago, I got a big funding grant about 3D printing, and we spent 5 years in understanding how we can print polyesters in a good way. Of course, it's easy to print, but the problem is that you degrade them while printing. We try to understand how to print and how the printing process influences the polymers. So I will tell you a little bit about that during the lectures as well. And normally we work with those degradable polymers, and then we collaborate with people that can do the cell material interactions. Because I don't have the biology background, even though now I have worked with cells for, I don't know, perhaps 20 years. I don't feel that I'm the expert. I want to collaborate with experts here. So we collaborate, and then we have some final prototype in mind. And during this big project, we actually had breast tissue as the aim to this first synthesize the polymers that could be printable and that could have the right properties for breast tissue regeneration. And then I'm not talking about hydrogels. I'm talking about something that can be used instead of silicone implants. Something that was more having other properties. I'm coming back to that also during my lectures. But basically, I'm only interested in breast tissue regeneration. It can be any type of tissue regeneration. I've worked a lot with bone tissue regeneration as well. It just depends on who I collaborate with, and then we design the polymers and do the printing with them. And I'm also part of, and I just want to mention this competence center, Additive Manufacturing for Life Sciences, that is based in Uppsala, just outside Stockholm, where there are a lot of partners working with finding new ways. It's both ceramics and polymers in this competence center, and a lot of companies where the mission is to develop, provide, and support a future supply of competence, technology, and spin-offs in additive manufacturing for the life sciences. And there are, especially for our interest, 3 work packages. There is biomaterial and process development, bioactive systems and devices, and bioprinting and biological interactions. And Professor Kutte has been visiting this competence center as well and been part of a course, actually. It's a nice competence center, so I think it's good for you to know about that. And also within the competence center, we have a lot of different 3D printers. So also, if you're interested in some kind of collaboration around this, you're welcome to contact me, and I can give you contacts into that competence center. But let's start with the lecture for today. So I know that I have approximately like 45 to 60 minutes, right? Something like that. But I won't rush through this lecture now. I will take it quite calm, so we understand. And then if I'm not ready, then we can continue with the same lecture in the afternoon. Right. So we'll see where we end up. So don't hesitate to interrupt and ask questions as well. And we will start with this question, what the polymer is. So who of you would say that you know what the polymer is? Sorry? Yeah, sure. Does everyone know? Understand that it's based on monomers? Yeah? Okay. So this is how I would actually like to divide the polymer into macromolecule and polymer. For me, that is actually a difference there that we need to consider. And I don't think that we in the literature and when we discuss actually differentiate that enough. I mean, we're talking about polymers more or less all the time, but we should talk about macromolecules in some ways. So what I mean with macromolecules is that you have a molecule. It can be then monomers, of course. We can call it monomer. And then we put them together and create a macromolecule. And then when we put many of these macromolecules together, that's when we create the polymer. And that is, sometimes we say that it's like a spaghetti dish or so. It's a nice way to consider what the polymer actually is. Also important is to remember that this macromolecule, these monomers will be different, and the macromolecules will have different length. If we're good and have a good synthesis procedure, then the macromolecules can be of the same length, but it's not that often. They will vary. Some will be short, some will be longer. And what we then say is that the polymer has a dispersity, and we get the number, and then we can understand how much it varies in length. But it is the macromolecule that varies in length, not the polymer as such. The polymer has a dispersity depending on the macromolecule's different length. Perhaps I should stand on the other side, then I can see where I actually, what the next slide is. Do you know the difference then? If you have a polymer, the difference between a thermoplastic and a thermoset? You know? So the easiest way to describe it is that in the thermoplastic, you just have these macromolecules laying around, while in the thermoset you have cross-links. You connect these macromolecules together. And this is important also for, I mean, sometimes in 3D printing you use the thermoplastics and sometimes the thermoset. And if you're using the thermoplastic, then you can use it again. You can recycle the polymer. While that is at least much more difficult. You cannot just do it as such if you're using a thermoset. So we have a few words here now. Macromolecule, polymer, thermoplastic, and thermoset that we need to have in mind throughout the course. Another important property is amorphous polymers and crystalline polymers that we need to understand what it is. So in amorphous polymer, all these macromolecules, they are just randomly distributed. There is no order whatsoever. They are just relaxed, randomly ordered. I can only describe it like that. In comparison to a semi-crystalline polymer, then you have these parts of the polymer where it's very ordered. You can see that these macromolecules, they are laying close to each other. They are ordered. And when they are ordered, we say that they can crystallize. Normally, a polymer is never 100% crystalline, so you have both amorphous parts in between, and you have the crystalline parts. And why is this important to have in mind? Yeah, it is important because if you compare polymers to metals, in metals you have a melting point. You say it's quite easy to define a melting point. For polymers, that is more tricky, especially if they are amorphous. Then the polymers goes from a glassy structure, and then it becomes softer and softer until it becomes a melt. So you start at the glassy state, and if you increase the temperature, if we look into the modulus, then the modulus decreases. It reaches the rubbery state, and then in the end you become viscous flow. And it's important that all of you understand what this glass transition is between the glassy state and the rubbery state. It is where larger segments of these macromolecules can start to move. So when you increase the temperature, if we have low temperature, they are very stiff. You cannot move. The macromolecules, they just stay as they are. If you increase the temperature, at some point, it starts to move. And when the longer segments move, then you have reached the TG. And I will describe how we can define and characterize the TG. But you need to know what TG means, especially when during 3D printing, because that will be important for setting the right parameters, right? So to summarize, I mean, it's only the amorphous polymers that have the TG. The amorphous polymers does not have the melting point. While the crystalline polymers, they have a melting point. It is the crystalline parts that melts. And it also normally have a TG, where the amorphous phase shows the TG. It's very different from the metals, that all metals have the melting point. That is not the case for the polymers, right? Do you follow? Yeah? So now I won't stop, but when I normally have a lecture, we stop and discuss these words. I won't do it now, but this is something from now, I mean, the first part that I want you to understand and be able to describe what the polymer is, to describe what the TG, the glass transition is, and also describe what the crystalline and amorphous polymer is. It's kind of the basics for the coming lectures as well. You have an idea about this. Yeah?
Thermoset and thermoplastic.
Yeah?
You said that the thermoset is recycled.
No, not the thermoset, the thermoplastics.
Thermoplastics are recycled.
Yeah.
So in the 3D printing, because there is always an objection, like you are using plastic, so whether you can recycle it or not. That's what exactly many times the query comes to us.
Yeah.
And
yeah.
we especially found in developing countries like India, like non-laser based 3D printing is easier for us to operate rather than the laser based, and therefore we focus more towards the FDM, that is the fused deposition modeling. So they say that the ABS plastic we use for getting the models and all that, but recycling, whether it will be possible with the ABS plastic that we are using.
I think that is something that we're looking into.
Yeah.
That comes in research. I don't know if it's possible now, but I'm part of research applications where that is something we have in mind, to understand how to recycle and use it again, and how that also influences the properties of the ABS or the PLA or whatever, which polymer you're choosing to have. So I think that will be an important next step in the field for sure.
Because they always nowadays the environmental issue is a very important issue in every engineering or any application.
Yeah.
So when I show them that there are so many models we have created and this is what we are doing it for surgical planning, whatever it is, those who are from the other, not from the technical side, they say that you are creating so many plastics, so whether you are recycling it or not, so that becomes a major issue.
Yeah. I know that they are already today, I mean the powder-based 3D printing, there you reuse the powder.
Powder-based, about that metal powder?
No, you can use polymer as well.
Polymers?
Yeah, yeah. I will describe that as well. I think it's the third lecture about that. So that I know it's already done. But for the other, for fused deposition modeling, etc., I think it's still research. Yeah, research on that. Of course you can. I mean, it's not a problem to do it. It's just to understand how it influences the polymer and the product properties in the end. Right? So that's what's interesting. But thermoset, for the laser-based things, I mean, then you have created crosslinks, and then it's much more difficult to. I mean, you need to break these crosslinks in order to be able to reuse it. Okay, but how can can we then tune? Because normally when we start 3D printing, or at least when I want to develop something for a special application, there is an aim for properties that is difficult to reach using the commercial ones. So we need to synthesize new ones to get new properties. And that is what I think is fun, to tune the properties. And just briefly how we do this, so you have an idea also about the possibilities. So we can tune the polymer properties by using the macromolecule, and then we can change the length, microstructure, chemical structure, and architecture. And just let me go through that in detail a little bit more. So if you have a macromolecule, of course, I mean, you can, as I said, have different lengths of these macromolecules. And depending on the length, you will also get different mechanical properties. So if you, for example, want to print ABS, and then you buy ABS, I mean, you also need to consider which molar mass this ABS has. Otherwise, you will get different properties. So ABS and ABS is not the same thing. You need to look more carefully into that. And that is because there is forces between the molecules and also between the macromolecules that is important. But also important, if you have a longer polymer macromolecule, is that you will create entanglements at some point. And those are super important for the properties. And you define the entanglements as when the chain crosses a plane 3 times. So if this is the plane here, you can see that it crosses here 1, 2, and 3 times. And then you have started the entanglement. And if they start an entanglement, the properties will be very different. And the tricky part here is that these entanglements occur at different molar masses depending on which polymer you're using. So just look at this. So if you have polyethylene, for example, you just need a molar mass of 4,000 in order for it to start to entangle. In comparison to if you use polyvinyl alcohol, then you need a molar mass of 25,000 before it starts to entangle. So you need to have this in mind when you work with the polymers. And this is why it's so important. And this is also a bit tricky part when you then do the printing, because this is the viscosity on the y-axis, and they have the molar mass on the x-axis. And then you can see that the viscosity is quite low at lower molar masses, but at one point it increases drastically, and that's where it starts to entangle. So for printing, it might be easier to be here. The molar mass is lower, so you get a more viscous and it flows better. But for the end use and the mechanical properties of the product, you want to be here, because then you get better mechanical properties. So that you need to have in mind, and it's dependent on just on the length of the macromolecule. And then the density is also important for the properties, and is also dependent on the molar mass, the branching, and the side group. And the viscosity, is dependent on the molar mass, the temperature, and the shear rate. I will come back to that later in the lecture. And then the length will also, as I said, be important for the mechanical properties. So if you have higher molar mass, you will increase the number of entanglements, you will increase the density and viscosity, and it will influence the flow during the manufacturing properties. And the problematic, I'm just, it feels like I only see problems, but the challenge, or what is important to remember, is that depending on which polymer you're using, this will vary a lot. We'll come back to that as well. And then in order to tune the macromolecular properties, you also have the possibility to look into the microstructure, the chemical structure, the monomers by themselves. So the atoms in the backbone, the size of the side groups. So if you, for example, have a side group here that is very bulky, it will make the chain, it will be more difficult for the chain to rotate, and that will influence the properties. Also, if you have ring substituents or something like that. If you have an oxygen instead, here for example, instead of the carbon, then it will make the chain it will rotate easier. So here you also have the possibility to design the properties by choosing the right monomers or different monomers. And then the architecture of the macromolecule itself. I mean, here's just a few examples that you have a linear. Normally we think of a macromolecule as just a linear chain, but that is of course not. It can be like a star. It can be like a cone where you just have the main chain and then you have side chains from that. And it can be any kind of branching structure, like a randomly structured branching. And all of this you can tune by the synthesis methods and also the monomers you are using. And that will influence the properties and the result in printing and the end product. So when we're tuning the polymer properties, we can look into the length, the microstructure, the chemical structure, and also the architecture. But we can also look into the polymer itself. For example, if you have many, or if you put the macromolecules close together, there will be interactions between them. Right? And depending on what the macromolecules, which monomers you're using, these interactions will vary. So the chemical bonds between the atoms or between the macromolecules, and the physical entanglements not only just within one macromolecule but also between the macromolecules will be important. And then you can tune the properties by looking into the crystallinity and the dispersity. So there are actually quite many ways that you and I can tune the properties of the polymers that we need to have in mind, which I think is fun. But that is, for polymer chemists, that is super good. So you can both look into the polymer, the process that we will discuss a little bit more, and the design. And all these three layers we need to consider in 3D printing. So it can be a little bit frustrating sometimes when I read papers and they say that, okay, when we print the PLA, then you get this result. Or this printed structure of PLA has this property. And to me it's like, okay, but I can vary those properties very easily. Just by changing the design, for example, I will reach totally different properties. So have that in mind when you're reading, that it is true for what they have printed and which molar mass they have used, and the copolymer or polymer, but it's not true for all, I mean, polylactides, for example. So that you can also think of to discuss later, how to tune the polymer properties and how you can tune the properties of the product. Do you follow? Yeah? Good. So then let's look into properties and how to characterize those properties that are important in additive manufacturing. And one of the most important properties is the molar mass and the dispersity. The molar mass of the macromolecules or the polymers. And that we normally evaluate by using size exclusion chromatography. How many of you have used this method? I see one hand only. How many of you understand or know what this characterization method is? How it works? Only one. But that's okay. Then I just know that I will just talk about it in more detail. If all of you have used it and know, then I don't have to explain that much. Okay. So what this technique is about, the characterization, is that you have your polymer, you inject it, and it goes through columns. And this is the drawing of a column. that is, you can see that it's column with a lot of particles. It's like a gel. And then here is your sample. It is injected. And then, depending on the size of these particles, the green ones are particles, these, and also the size of your macromolecules, it will take longer or shorter time for the macromolecules to go down. So there is a natural size separation here, that the red one, that is the larger particles or larger macromolecules, will go through this column faster, while the small ones, they will enter into each pore. So there is a natural separation here, that the larger ones, the red ones here, comes through the column first. The green one, that is a little bit larger, it will take longer time. And the blue one, that is the shortest macromolecules, will take longest time. And in that way it will separate. And when it comes out, there is a detector. It can be different kind of detectors. I don't need to go into detail there. But that show us which kind of I mean, what size the particle has and how many different particle sizes they have. And then we get the value of the molar mass, both all the kind of molar masses, like number average and weight average, etc. But also important here to know is that it's not the absolute molar mass that you will get. It's actually the hydrodynamic volume that you actually get. Because the macromolecules, they form these particles, and it is the particles that goes through, and that is what is detected. And then sometimes there is possibility to take that value and get it into absolute numbers. But that is also dependent on the polymer and the column as such. So you need to be careful there. And normally when we report the data, we just report the data that comes out from the column. And also the dispersity we will get from this, and that will be dependent on how broad these peaks are. If they are broader, then there is a higher dispersity. Normally, if you synthesize polylactide, for example, and characterize that in SEC and do it good, you only get one peak. And that peak can be broader or it can be more narrow, depending on the dispersity. So I don't normally get three different peaks. But it's just the method here that I want you to understand. So just to summarize, you have a column, you have particles, and then these macromolecules are formed into spheres, and those go through the column at different rates depending on the size. Okay, so another property that is important in additive manufacturing is thermal properties. Because there is a temperature where you will be able to process the polymer. I mean, if you're working with gels, I mean, normally and cells, we normally work in room temperature. But if you're working with polyesters or other polymers, then you need to increase the temperature so you get the viscosity so it's printable. And then you need to define which temperature to print. And that temperature should be between the melting point and the onset of thermal degradation. Because you don't want it to start to degrade. But you need to be above the glass sensation temperature so it has started to move, but then not degraded. And you need to define that before starting. Well, I mean, it's possible to print anyway, but it's good to have an idea so you don't destroy your polymer work. And for defining at which temperature it starts to degrade, we're using the TGA, thermogravimetric analysis. And basically what that is about is that you have the weight here of your sample, the polymer, and you have the temperature here. And then you increase the temperature, And at some point, the weight will start to decrease. And that is where the polymers start to degrade. In this case, there are different materials. You have polyesters, you have styrene, and you have fiberglass in calcium carbonate. So that's why it starts to degrade at different points. So that can also define. But it's quite easy to do. Actually, you just have a cup, you add your sample, increase the temperature, and look into how the weight varies. And it's important to know. Okay, so if you're having the polyesters, I don't know what this is, but say that it's 300 degrees. Then you should be below that if you don't want the polymer to degrade while printing. Of course, you can also do it like this, that you print, and then afterwards you test the polymer in the size exclusion chromatography, the method I just described, and see and compare the molar mass. I mean, that is of course also possible. But I think this is easier that you know beforehand when it starts to degrade. And the TG and the melting point and crystallization temperature we normally characterize by using DSC, differential scanning calorimetry. Have you used that? A couple of you have used it. There are some equations here, but I won't go through it in detail. But what this method actually does is that it looks into the material's heat capacity and how it changes when we increase the temperature. So when we go through the glass transition temperature, the CP, the heat capacity will also change, and that is what is valued by the heat flow. There is actually a nice movie if you're interested into this characterization technique. And if you're interested in that, I just send an email. I can send you this link. I won't show you that now. But again, what we do is that we have a reference, we have a sample, and then we increase the temperature, and we evaluate the heat flow. Actually, it looks like this. You have the heat flow, and you have the temperature. And when we heat the sample, at some point the heat flow is increased. So this means that the amount of heat that is needed here to raise the temperature is higher compared to here. So there is a transition here of the material that is detected. And when it looks like this, we call it is the glass transition temperature. So just to repeat that the difference here is how much heat that is needed to raise the temperature 1 degree. And if we go to even higher temperature, what happens here is that you have the TG, it looks here, and then at some point when you have reached the TG and the segments, the polymer starts to move, they can also start to organize in a better way. Suddenly they are not stuck in the position, they can move, and then they can start actually to crystallize even more. And that is what is shown here, the crystallization. And that is an exothermic transition. And then if we increase the temperature even more, we reach the melting point. Then we can see also that the CP value varies and the heat flow needed increases. And then the polymer starts to degrade. So this is the curve above is for a crystalline polymer and amorphous, semi-crystalline I should say. The one below is for the amorphous polymer, where we, as I said, we don't have a melting point, we don't have any crystallization, we only have the glass transition temperature here. So what you do also in the DCGS more practically, so you have a cup, you add your sample, you put it into the machine, and then you decide where to start, with which temperature to start and where to end, and at which rate you should increase the temperature. Normally we also do like this, that we heat it, and then we cool it, and then we heat it again. And the values that we report is from the second heating, because then we know that all our samples, we have the same thermal history. They have crystallized under the same conditions. So when we heat it again, it will be possible to compare different samples. When I do it for my printed structure that I also use for cell material interaction, I use the first heating scan, because that is what actually the cell will feel. So you can use both. It's not that you need to use the second heating. You need to think of what you're actually aiming for. And looking at this curve, the DC curve, if you have a single crystalline polymer, you can also calculate the crystallinity, which we also normally report, and which is also good to compare between different polymers. And what you then do is that you take the area under the melting point, you subtract the area under the crystalline peak, and then you divide it by the value of what it would be if it was 100% crystalline. And those values you have tabulated for most polymers. You can find that. And then you can report the crystallinity, which is good when you're comparing polymers or scaffolds, etc. Because your scaffolds, depending on how you cool them, when you have printed them and cooled them, the crystallinity will vary. So even if you have the same polymer, you have the same molar mass, you print them in the same way, but you cool them in different ways, the crystallinity will vary. So it's a quite important property to actually report after the printing. And I just showed a few examples of polymers that is normally used in 3D printing, the ABS for the lactide and the PA. And how the TG varies. Or in ABS you have the TG between 110 and 125. PLA has around 55 to 60, and the PA is 60. And also that the melting point varies. So we need to have these values in order for start printing. And the degradation when it starts to degrade. But how do we then make the polymer printable? And what actually makes the polymer printable? Okay, so it's quite obvious that the polymer needs to be able to be extruded through the nozzle. When we have extruded, we also want it to hold its shape. We don't want it to flow out if we have made a very complex structure. Normally we use gaps when we print, and we want it then to be able to bridge that gap. And all these together is controlled by the polymer's rheological properties. And rheology, I mean, that could be a course that we could have for 2 weeks, I think. It's a very, for me, complex area, and a lot of details that we need to understand. So I won't do that, I will just show a couple of slides. But I want you to remember that rheology is super important for understanding how the polymer behaves in the printer. In one of the lectures, I will show how we have used the rheometer and the rheology properties in order to understand different polyesters and polycarbonates. But just to give you an idea here, and there was someone in material science here, and normally those students have normally used this a lot, the rheology, and understand the shear rate, shear stress, and shear viscosity. But just for all of us to have an idea. So the shear rate, then you have the rate divided by the height. If you have the shear stress, if we're talking shear stress, then you have a force divided by the area. And then if we talk about shear viscosity, then you divide the shear stress with the shear rate. I will come back to those in a second. Just in between, I want to say that the flow properties in regard to the rheology, we need to remember that that it can go either Newtonian or non-Newtonian fluid. And for a polymer, we're normally having the non-Newtonian property. And with that means that the viscosity depends on the applied shear rate. So if you have an extruder and you force the polymer through that, it will influence the viscosity. And also that the viscosity depends a lot on the molar mass. A little bit problematic is that the polymers are normally also viscoelastic. So it can both behave like a liquid, so that it means that it continues to deform when the stress is applied. But it's also like an elastic solid, so it can actually recover some of the deformation. And these two are also tricky, and we need to understand. And also, if you have tried to print polycaprolactone and compare it to polylactide, you know the difference between the melt elasticity, where the polycaprolactone is, even though it's in some way easy to print, it also has a high melt elasticity. So it can, in the nozzle, it can actually curl, and it can be difficult for it to start to print and adhere. And that is related to the melt elasticity in comparison to polylactide that has a lower melt elasticity. So we need to also have in mind that it's non-Newtonian and also that the polymer is viscoelastic. And I also have a few movies which I think actually explain the rheometer and the rheology in a quite good way. Some YouTube films that I can give to you if you're interested into this area. But just to show you that it is important, here you have the apparent shear stress, and here you have the shear rate. And dependent on which shear rate you're using, the shear stress will vary, and also dependent on which temperature you're using. So you need to choose a temperature, and then you need to look into which speed should I use in the printer, and that will influence the shear stress. And that of course will also influence not only how easy it is to print, but also which product you get out. If you get if you have a higher shear stress, that will influence the polymer in one way compared to if you have a lower shear stress. So the flow properties is important. I'm coming back to that as well in another lecture. But here is actually a good paper about that has summarized the importance of both the polymer rheology on material extrusion additive manufacturing, where they correlate process physics to print properties. So, a good paper for you to read that I will not summarize. So I think actually I went through now, took perhaps an hour, I don't know. But to summarize the basic words that I want you to have in mind, that is important for the rest of the lectures, and also the characterization method that is important for us to understand how the polymer behaves in the printer. But we also will come back to regularly during the lectures. And then this afternoon I will take this a step further, talking about shrinking and aging and degradation while printing. So I think with that, I think I'm satisfied for now. Any questions or discussions are of course welcome.
Yes.
Yes.
No, I have questions.
Yeah.
Like interesting that when you mentioned that you can vary the polymer's properties by there are many methods like by length, architectures. So I'm quite curious that how we can vary the architecture, like to vary the planes or the entanglements you also mentioned. So what is the process to vary the architectures?
It's just, synthesis method, depending on which monomer you're using. The easiest way, if you want to use, for example, a branched polymer, is that you can synthesize linear ones, and then you use radiation. You radiate on the macromolecules, then you will create radicals. And from those radicals, you add more monomers, and then they can start to build these side branches. Yeah.
So it is controlled or like
Yeah,
arbitrary?
it can be controlled. It can be controlled. It can also be that normally you have an initiator when you start the synthesis, and instead of just a linear initiator, you can use like an initiator that has 4 functional groups. So it starts to grow on all these 4 arms, or you can have 6 or 7 or whatever. Then you get like a branched structure. So they are quite easy to do actually. But you said something else on not only the structure. You said some. No, oh sorry. You can.
Ma'am, and another thing you mentioned that this transition glass temperatures and for semi-crystalline polymer, there is also melting temperatures. So means for viscous flow that you also show that in the graph is rubbery stage, rubbery flow, and there's the viscous flow stage. Then there's the degradation also. So what is the most important? Like this transition glass temperatures while printing, what we should keep remembering in our mind that or the melting temperatures.
I would say the melting temperature. That normally we are about the melting temperature in order for to print, to get a good flow.
Because then sometimes I am not sure about the polymer materials, like melting temperature is not that like for degradation temperature we quite often use with degradation when the polymers or hydrogen so degrades. It is most important. But for this case, melting temperature is important for poly display.
Yeah, I would say. And you want to be somewhere between the melting temperature and the degradation temperature. But then while cooling, you can adjust a little bit. Then perhaps you want to be closer to the TG in order to optimize the crystallinity of your printed product. So in that sense, it is important. And also, the TG is also important in that sense that where and when you can use your scaffold in the end. See that you have a TG of 5 degrees, then you cannot use it in room temperature. So you need to use it for that sense.
I have a question. When you shared your experience about when you read research papers, the authors mentioned that PLA properties as an outcome when they mention about the PLA properties, and you said it's frustrating because you can change the PLA property by designing it. So when I am writing a research paper, so my question is, if I am writing a research paper and I am mentioning if I am using that one particularly designed PLA, so is it okay to mention it in the research paper, or it will raise a question for the editor that why I am using that one particular design PLA, or should I mention or explain that why I am using with the comparison of other designs?
I think it varies between persons if they care or not. I think it's super important. Or I think it's very interesting to understand why you have chosen a specific design.
So should I mention that in paper? Is it good, or should I create a comparison between designs? What should be the approach I should follow that?
I think there are different, what you're saying is 2 different research questions. We have papers where we have varied the design and look into the properties, both modeling and practically, and also look into how the cells adhere and interact with different designs. So that was like a research question. But I also have papers where we only used one design because those properties were suitable for the application that we were aiming for. So then in that sense, it makes sense to only use one design. But then we say that, okay, we use this because it has a property that is important. It can also be that you just want to see how the polymer behaves. It's not really the property of the scaffold itself you're interested in. I mean, that can also be fine. Just as long as you're clear for what the aim is and not just stating that this polymer scaffold will kind of always have this property, if you see the difference.
This characterization methods that you have mentioned, is it to characterize the polymer that you create in the lab?
Yeah.
So ABS or PLA, if we take for 3D printing, it comes in a wire kind of format. So it will have some different mechanical properties in that form. And once we print it, based on maybe the print speed and the layer orientation and everything, the component will have a different mechanical characteristic. So is there any, can we relate the polymer properties with the component that we finally print? So the strength in polymer form, can we relate it to the strength of the component where we actually print it?
Do you then mean like the bulk properties of your printed scaffold?
Yeah. If we see the mechanical parallel, we have steel properties, its Young modulus Poisson ratio. But then if we make a structure from steel, then it will have a different stiffness. But that stiffness will be related to its Young modulus and density and everything. So does similar things happen in polymers also?
Yeah, for sure. And that you can characterize as well.
Is there a session on this in this course?
I don't know like a session as such, but I will bring up our results, how we experienced how the polymers
or maybe you
behaves.
can just point me to the literature which discuss this also.
Yeah, but do you then mean that, I mean, there are so many different kind of information. So the mechanical properties of the scaffold in comparison to the filament.
Yes.
Yeah, but let's see. Perhaps I can do that. I don't know really if it's so often compared in the literature. Actually, if they do the filament and then normally they just report the scaffold and the properties of the scaffold and not the filament. And I think that is a problem, especially since the polymer changes.
Yeah.
But normally perhaps the end product is almost just for people, so they just show that. But let me think. It might be. Remind me again if I forget. Yeah.
Is there a way to differentiate amorphous and semi-crystalline polymers other than melting point?
To differentiate, I mean, amorphous polymers won't have a melting point.
Other than the melting point, is there any other effect to difference? Like chemical bond or functional group characteristics? And
No. Good question. I've never used anything else, but of course you can, by looking into the design of your macromolecule, you can kind of discuss around that this will be amorphous because it won't be possible for it to crystallize.
which kind of bond or functional group
Yeah, exactly.
generate the crystallinity property?
Yeah, I mean that is, but I wouldn't. I mean, in a research paper, I don't think that I would. Claim that I would then do the measurements and show that. But beforehand, you can of course have an idea that this won't. And you can also use modeling or calculations, etc., to look into that. So perhaps that is the best idea to do some calculations and modeling. Look into that if it's it's possible for it to rearrange and organize in that way that it's possible to
For
crystallize.
processing, we can shift chemical environment or introduce a different type of bond to generate a semi-crystalline polymer from a
You mean you can do that?
Means if we can do that by introducing a different chemical bond or functional group into the polymer, so that we can generate a different class of semi-crystalline polymer from amorphous.
Yeah, of course, you can do that. And you should also remember that depending on how you cool the polymer, you can create more or less crystallinity. If you cool it very fast, then it won't have time to crystallize, so then you will get more amorphous polymer.
That means what changes? What raises the crystalline?
Sorry,
Means what changes in amorphous to introduce the semi-crystalline?
so if you want to have a more crystalline polymer, then you need to have more. I mean, you don't want to use bulky side loops or branches or things like that. You want to have. I mean, the best way is to have linear macromolecules. Yeah, with the same molar mass as structure as possible, and give it time to crystallize during cooling.
It's only the physical characteristics, or is there any chemical characteristics?
You mean chemical characteristics?
Means you can say that.
Or you mean, for example, that if you I mean, if you're meaning that if you introduce oxygen into the macromolecule, then it will be easier for it to
More
rotate.
crystalline, or it will be more amorphous.
Then it will be more easy for it to rotate, right? So then you can think of that, okay, but then it will be more easy for it to reorganize and have a high crystallinity.
Instead of depending on the temperature, can we depend on the chemical properties of the polymer for crystallinity?
What do you mean now?
Means generally we use temperature whenever we say that there is a crystalline or melting point, or semi-crystalline there is a melting point into crystallinity or part. Now that's only the temperature. Means there is only a temperature that we depend to see there is a crystallinity or not. Now before or instead of using the temperature as an only parameter, can we use the general chemical structure to identify if there is crystallinity or not? Only looking at the chemical structure.
Again, I would say that you can discuss around that, but I don't think that you can characterize it from that perspective. I mean, of course, you can use mechanical properties as well to understand if it's more amorphous or crystalline, but only from the chemical perspective. I cannot see that there is a characterization methods to define that.
So I think we'll have a break for some time. I think everything is there.